is Ilya Josefson, and this video is here to describe a project that I worked on during my undergraduate career at Tufts University. This project initially began as an independent study project that I had begun outside of any classwork that I was taking. This project was initially funded by the NASA Tufts Fellowship in Space Science and Technology. There were a list of projects which one could get funding for. I chose the one that I was most interested in, which ended up being the automated control of a payload on its descent back to the Earth. I worked on this project during my sophomore year independently. During my junior year, I was able to work on this project as part of an inventive design course offered at Tufts University. During my senior year, I turned the project into my senior thesis, which I eventually received thesis honors for. Hope you enjoyed the video. A popular tool used in many types of atmospheric research is ballooning. A payload equipped with instrumentation is sent to high altitudes by a specialized balloon. Information is gathered and stored by the instrumentation found on board on the ride up. Once the system reaches a specified altitude, the balloon pops and the payload falls. A parachute is used to slow its descent on its journey back to the ground. A team is then dispatched to find and retrieve the payload by following a homing signal that it gives off. This type of system is open to many variables and is really quite inefficient. The payload may be taken far away from its launching point by high-altitude wind patterns. It may also interfere with obstacles found on the ground, two scenarios which make retrieving the system more difficult and expensive.
I came up with a number of solutions to the problem, three of which are pictured here. The simplest solutions involved a parachute and fins, while the more complicated solutions involved airfoils, fins, and even propellers.
I developed a decision matrix to help me decide which method of descent would be best to use for this project. I developed another decision matrix to help me decide which method of spatial orientation would be best for this project. At the end of the day, it was decided that a parachute with fins was the simplest, most cost-effective solution.
Then came the fun part, building and testing the prototype. The initial prototype only had two fins. I changed the orientation and angle of the fins just to test how effective each would be.
I recorded the path of each iteration of the prototype using a video camera. I then wrote a program in LabVIEW to help me analyze the footage.
The program tracked the payload capsule as the whole system fell to the ground. The program outputted graphs which tracked the motion of the payload capsule. I used these graphs to help me determine which iteration of the system worked the best.
A problem I noticed while testing the first prototype was very short flight time. Because of the short flight time, I was not able to test the algorithms that I developed for the system. Because of this, I had to change conceptual models. To do this, I bought a paraglider. I retrofitted the paraglider with parallax components. The circuit I developed is pictured here. It consisted of a GPS module and a compass module, which worked together to find the orientation and location of the system. 3 microprocessors were involved, labeled here as BS2s, which took that information and outputted the proper movement into the servo motor, which helped to control the parachute of the paraglider. All this data was recorded onto a USB data logger. During testing of the prototype, the paraglider flew into a tree and ripped the parachute. At this point, I was running out of budget and time, so I had to change the conceptual model into a ground vehicle. It is pictured here. At this point, I just needed to be able to prove that the components could work together to navigate the system properly.
Well, that was the end of the project, and although I was not able to come up with a marketable solution to the problem, I did show that with 2 different types of proofs of concepts, that the system I designed could be used in the future had I had more funding and more time to complete the project. Thank you for watching.